Hello everyone and welcome back to the course. Today we are going to keep on diving on operations on set theory, but this time we're going to dive into the properties of such operations. Now it is time to introduce the most important properties related to the union and intersection between sets. Let A, B, and C be sets. The most important properties are the following: the commutative law, the associative law, and the distributive law of the intersection with respect to the union, and also of the union with respect to the intersection. We encourage you to prove both the commutative and the associative properties. For now, we are going to prove the distributive property of the union with respect to the intersection. In order to prove that the union between A and the intersection between B and C is equal to the intersection between the union of A and B and the union of A and C, we need to prove that each of them is a subset of the other. Let us prove first that the union between A and the intersection between B and C is a subset of the intersection between the union of A and B and the union of A and C. Let us assume an arbitrary element X in the union between A and the intersection between B and C. Now, we have two cases to analyze. As X is an element in the union, then X is an element in A or an element in the intersection between B and C. In the first case, we are going to analyze what happens if X is an element in A. If such a thing happens, then by logical addition, we know that X is an element in the union between A and B because X is at least in A, and also is an element in the union between A and C because at least we know that X is an element in A. And therefore, X is an element in the intersection between the union of A and B and the union of A and C. Now, the second case states that if X is an element in the intersection between B and C, then by definition we have that X is an element in B and X is an element in C. Therefore, again, by logical addition, we know that X is an element in the union between A and B and the union between A and C, because in both cases, X is at least in B or in C. Hence, X is an element in the intersection between the union of A and B and the union between A and C. And therefore, the distributive law of the union with respect to the intersection is true. We encourage you to prove the other distributive property. You will follow similar steps as we did in this proof. Two other important properties related to both the union and the intersection between sets are the identity properties, which are the following. The intersection between A and itself is equal to A. The union between A and itself is equal to A. The intersection between A and the empty set is equal to the empty set. And the union between A and the empty set is equal to the empty set. These properties kind of work like the numbers 1 and 0 in both addition and multiplication between numbers. We encourage you to prove these statements. Now it is time to introduce a property related to power sets. This one states that if the power set of a set A is equal to the power set of a set B, then A is equal to B. Let us prove such a statement. We are going to prove that statement by using the contrapositive, which, remember, is logically equivalent to the conditional. we will assume that A is different than B. And we will prove that the power set of A is going to be different than the power set of B. Now, if we assume that A is different than B, then either A is not a subset of B or B is not a subset of A. Let us analyze both cases separately. The first case, if A is not a subset of B, then A cannot be an element of the power set of B, because remember that the power set of a set is made of all the elements that are subsets of such a set. And as A is not a subset of B, then A cannot be an element of the power set of B. But indeed, we have that A is an element of the power set of A. We know that both A and the empty set are always elements of the power set of A. Therefore, we have an element here, which is A, which is an element of the power set of A, but is not an element of the power set of B. Therefore, the power set of A is not contained in the power set of B. And therefore, the power set of A is different than the power set of B. Thus, for the previous two cases, we can assure that the power set of A is different than the power set of B if A is different than B, proving the contrapositive and therefore the original statement, meaning the conditional one. Finally, we will introduce the most important properties related to complementation, meaning the De Morgan's property, the identity properties for complementation, and the double complementation property. Let us start by proving one of the De Morgan's property, in this case related to union. We will leave the one related to intersection for the viewer. So we are going to prove that the complement of the union between A and B is equal to the intersection between the complement of A and the complement of B. We will do this proof step by step. Let X be an arbitrary element in the complement of the union between A and B. Then, by definition of complement, we have that X is not an element of the union between A and B. Therefore, as X is not an element of that union, then by definition, X is not an element in A and also is not an element of B. Now, if X is not an element in A, then it must be an element of the complement of A, and as well, X will be an element of the complement of B, because X is not an element of B, as the definition states. Therefore, we have that X is an element of the intersection between the complement of A and the complement of B. So, we are going to prove that the complement of A is equal to A. Again, we will do this proof step by step. Let X be an element of the complement of A. Then, by definition of complement, we have that X is not an element of the complement of A. And as X is not an element of the complement of A, then X must be an element of A. Thus, we can conclude that the complement of A is equal to A. This shows that the complement of a set gives back the original set. Well guys, this is all for today. Thank you very much for following this video until its very end. In the next and last lesson of this course, we will study counterexamples and how to refute general statements in set theory and therefore in mathematics. See you in the next lesson.